So we've seen deductive proof, most commonly done with our geometry. So we start with known facts, and from those known facts we deduce what it is we're trying to prove. Inductive proof, of course, we've seen quite a bit of now, and that's where we assume what it is we're trying to prove and induce a solution. You may remember proof by contradiction. We did that, I think one of the examples we did was proving the square root of 2 was irrational. And so that's where we assume the opposite of what we're trying to prove and then create a contradiction. So that once you've got a contradiction, you can say, well, hang on, my original assumption must have been wrong, therefore the opposite must be the case. So they're all different types of proofs that we've looked at. Now, some techniques when we're looking at these inequality questions. I guess the most basic idea is this. If you want to prove x is greater than or equal to y, quite often it's easier to prove x minus y is greater than or equal to 0. Because often it's easier to show something's always positive, or if it was a less than or equal to, always negative. So here's a very quick one, a very simple one, which comes from the 1995 paper, where they had to prove PQ was less than or equal to P squared plus Q squared on 2. So what they did is they moved everything to the left-hand side and said, notice there's no inequality sign at this stage. So this is just a piece of algebra. I want to show that this piece of algebra is less than or equal to 0. Because if I can do that, it then becomes a fact. And once it's a fact, I can then move terms around and create what it is we're trying to do. So if I turn that all into one fraction, the top of the fraction we now recognise to be a perfect square. And because it's a perfect square, I now know that that fraction is greater than or equal to 0. So I now know that to be a true statement. So if that's true, I can say, well, I've written it backwards to the way the question originally had, but I can move the PQ to the right-hand side, and we get P squared plus Q squared on 2 is greater than or equal to PQ. So that's a very simple case of, oh yeah, let's show something's always positive. I suppose I could do this, not suggesting you would. Let's do it by contradiction. Let's say, no, I'm going to assume PQ actually is bigger than P squared plus Q squared on 2. Now, if that's true, and I'm assuming this to be true, so I can move terms around, then 2PQ would be greater than P squared plus Q squared, which means 0 would be greater than, well, eventually when I factorise it, P minus Q all squared. Well, of course, 0 can't be bigger than P minus Q squared, because P minus Q squared is greater than or equal to 0. So we know P minus Q squared, well, in this case, greater than 0. I'm assuming P and Q aren't the same thing. So therefore, the reverse must be true. My assumption must have been false. So PQ is less than or equal to. I'd say it's probably not the way I would go and prove that one. I'd probably do it the first way, just show everything's positive. But you could use another technique if you wish to. Okay, let's look at some more interesting ones. So 1994, quite an old problem now. Prove a squared plus b squared plus c squared is greater than ab plus bc plus ac. I'm going to start with a known fact with this one and then manipulate that fact. And the fact I'm using is that a perfect square is greater than 0. So I know that a minus b squared will always be greater than 0. Now if I expand that out and then move the 2ab to the other side, I've manipulated that to become a squared plus b squared is always greater than 2ab. But of course, a and b are just pronumerals. That would be true for any particular letter that I wanted to put there. So it would also be true then that a squared plus c squared is greater than 2ac, b squared plus c squared is greater than 2bc. If I treat them like simultaneous, I suppose we'd call them simultaneous inequations, 2a squared plus 2b squared plus 2c squared, well, I can divide everything by 2, and there's our relationship. You may well have seen that before. As I say, it's quite an old question now. It comes up a lot in different textbooks and things like that. But building on that, we go, well, what happens if a plus b plus c equals 1? If that's true, we're going to prove that ab plus ac plus bc is less than a third. Okay, well, if I was to square a plus b plus c all squared, and then rearrange that expansion, we get this familiar result. At least I hope it's familiar, because it's no different to when we were playing with sum and product of roots. Essentially, it's the same fact that we're saying. Some of the roots squared is equal to some of the roots 1 at a time squared minus 2 times. So it's the same relationship I'm using there. So therefore, what do I now got? Well, a plus b plus c squared minus 2 lots of ab plus ac plus bc must be greater than ab plus ac plus bc. Where have I got that from? So going back to part A, where we showed that, well, a squared plus b squared plus c squared is greater than ab. So just substituted in. So rearranging that, I've got 3 lots of ab plus ac plus bc, which then becomes 3ab plus ac plus bc is less than 1, because we said a plus b plus c is 1, giving me ab plus ac plus bc is less than a third. Okay, which now brings us to this classic result, which ordinarily we can quote, unless, of course, it's what it's being asked to prove. So in this case, a third a plus b plus c is greater than or equal to a cube root of abc. All right, we've proven that a squared plus b squared plus c squared is greater than or equal to ab plus ac plus bc. So moving everything to the left-hand side, that's going to be greater than or equal to 0. If I multiply both sides of this by a plus b plus c, I've still got a true statement. Again, assuming a, b and c, in this case, now I do need to assume a, b and c are positive. Well, if I was to expand that whole thing out, that's what I'd get. Amazingly, it tidies up to be that. There's a lot of cancelling that happens in there. Divide by 3, move the ABC term over, and we've got something that's close to what we're trying to prove. But remember, A, B and C, they're just random pronumerals. So how about I let A be the cube root of A, and B be the cube root of B, and C be the cube root of C, and I'll substitute that in. Well, there's no reason I can't do that, because remember all we said about A, B and C were they were positive numbers. So A is any positive number I like, so I could make it the cube root of A if I wanted to. And that gives us our particular result. That idea that we just proved there is that the arithmetic mean is always greater than or equal to the geometric mean. It's a classic result, which is used quite often in these proofs. So to say, unless it is what they are asking you to prove, you can just quote that and go, oh, well, because arithmetic mean is greater than or equal to the geometric mean. Okay, let's keep going with this one. Just suppose that 1 plus x times 1 plus y times 1 plus z is 8. We're now going to prove x, y, z is less than or equal to 1. I think this is the one I did a couple of ways. The first way is fun. You're going to love this. 1 plus x times 1 plus y plus 1 plus z. Let's expand the whole thing out. Okay, so we now know that that is equal to 8. I know that a third of x plus y plus z is greater than or equal to the cube root of x, y, z. Arithmetic mean greater than or equal to geometric mean, also what we just proved in part C. Another way of saying that is x plus y plus z is greater than or equal to 3 times the cube root of x, y, z. Well, if that's true, instead of x I could have xy, instead of y I could have yz, and instead of z I could have xz. All I'm saying is the sum of 3 things is always greater than or equal to 3 times the cube root of those 3 things multiplied together. And I can put anything in there for those things. Okay, so that therefore means that xy plus yz plus xz is greater than or equal to 3 times the cube root of x squared, y squared, z squared. Now remember we said this. 1 plus x plus y plus z, etc. is 8. Therefore, this expression must be less than or equal to 8. And I don't know, if you can't see it yet, let me do that. I'll change xyz to be the cube root of xyz cubed. 1, 3, 3, 1. 1 plus the cube root of xyz all cubed is less than or equal to 8. I told you you're going to enjoy that one. Just find the cube root of both sides. Move it over. And voila! So that's the really cool way of doing it. Okay, I'll show you another way. You boring people will go this way, I suppose. It's only a little bit quicker. One, but not just a little bit. 1 plus x will be greater than or equal to 2 root x. Arithmetic mean greater than geometric mean. So two things added together will be greater than or equal to two things times the square root of those two things multiplied together. Same is true for 1 plus y. Same is true for 1 plus z. If I add them together, I get 1 plus x plus y. Oh, hang on. So 8 is greater than or equal to 8 root x, y, z. Okay, it was a little bit quicker. Just a little bit quicker to get to the bottom. All right. Well, let's try this one then. 9 on a plus b plus c is less than or equal to 2 on a plus b plus 2 plus on b plus c plus 2 on a plus c, and that's going to be less than or equal to 1 on a plus 1 on b plus 1 on c. Arithmetic mean, geometric mean, but you'll notice I've done two of them. The first one there is a plus b is greater than or equal to 2 times the square root of ab, so we know that to be true. And 1 on a plus 1 on b will be greater than or equal to 2 times the square root of 1 on ab. Therefore, if I multiply them together, that should be true. So I now know that a plus b times 1 on a plus 1 on b is greater than or equal to 4. So 1 on a plus 1 on b would be greater than or equal to 4 over a plus b. Okay. Well, I could have done b and c. I could have done a and c as well. So if I add them all up, 2 on a plus 2 on b plus 2 on c greater than or equal to 4 on a plus b plus 4 on b plus c plus 4 on a plus c. Divide everything by 2 and we have the right hand side of what we're trying to prove. Okay, let's do the left hand side, where I'm going to do exactly the same thing but now with all three terms. So I know that a plus b plus c will be greater than or equal to 3 times the cube root of abc, and 1 on a plus 1 on b plus 1 on c will be greater than or equal to 3 times the cube root of 1 on abc. Those two surds will multiply together and cancel out, and we get 9. Therefore, how quick was that one? 1 on a plus 1 on b plus 1 on c is greater than or equal to 9 on a plus b plus c. Only one problem. What about the middle bit? Yes, we've proven that 1 on a plus 1 on b plus 1 on c is greater than or equal to 9 on a plus b plus c. We've also proved it's greater than 2 on a plus b and so on. But what's to say that the 2's in the middle, why couldn't it be the other way around? Well, all I do, I'll just replace a with a plus b, and b with b plus c, and c with a plus c, and voila! Look at it closely. I've replaced a with a plus b. So the first fraction becomes 1 on a plus b. The second fraction becomes 1 on b plus c and so on. So on the right hand side, a plus b plus c would become a plus b plus c plus a plus c. So we have two lots of a plus b plus c. Multiply both sides by 2. We now have that middle bit that we want. So therefore, we have trapped it in between. Are we having fun yet or what? Okay. Wow. A is a real number. This time I've actually specified it. And it's going to be positive. We have to show that a plus 1 on a is greater than or equal to 2. Again, I'm going to use arithmetic mean, geometric mean. So a plus 1 on a will be greater than or equal to 2 times the square root of multiplying them together. Well, a times 1 on a is 1, so we get is greater than or equal to 2. Bingo. So that bit was quite straightforward. Of course, another way I could do that. I know that the square root of a minus 1 on the square root of a squared will always be positive. So I'm starting with a known fact there. If I expand that out, I get a minus 2 plus 1 on a is greater than or equal to 0. Move the 2 over, and there's our result. Another way I could have done. So the first bit, arithmetic mean, geometric mean, etc., is hopefully giving us a hint for part B. because now A is greater than 0, B is greater than 0, C is greater than 0, we're going to show that B plus C on A plus C plus A on B plus A plus B on C is greater than or equal to 6. But what we know is any number plus its reciprocal will always be greater than or equal to 2. That's what we've basically shown. So therefore, B on A plus A on B will be greater than or equal to 2. So C on A plus A on C will be greater than or equal to 2. C on B plus B on C will be greater than or equal to 2. Add them all together and look what we get. Now if we group together the ones with the same denominator, you'll see that we have B plus C on A plus C plus A on B plus A plus B on C is greater than or equal to 6. So with a lot of these inequalities, it's just playing around with arithmetic mean, geometric mean. Now we're going to show that A on B plus C on C plus A plus C on A plus B, so the reciprocal, if you like, is greater than or equal to 3 on 2. Well, because we just proved B plus C on A plus C plus A on B plus A plus B on C is greater than or equal to 6. We just proved that. All right. Well, let's let A equal B plus C, B will be A plus C, and C will be A plus B. And substitute that in. And look what we get. For the one with B plus C on the bottom, we get A plus C plus A plus B. And then the next one becomes A plus B plus C, and so on and so on. So we've got 2A on B plus C plus 1, plus 2B on A plus C plus 1, plus 2C on A plus B plus 1. But all of those plus 1s I can move to the right-hand side. And if I divide everything by 2, we have our result. All right, now we got in the handout there's an inequality sheet in there, which I'm pretty sure has solutions with it too. So you might find that one handy. In Cambridge, it's the 10B. In book 1, Real Cambridge, number 28.